So when we're talking about graph theory in this class, what we're talking about is things like this. Systems of vertices and edges, points, lines, connections between points that can talk about representing places on a map, people with connections between them, or just very abstract structures where you're interested in how these different sorts of things may or may not interact in some meaningful way. Where I will point out here, just to be sure, that this type of thing is not necessarily the sort of thing that probably comes to mind when you think of a graph in math. Something like a bar graph or the graph of a function, that's not really what we're looking at here. That's not the sort of relationship we're trying to discuss here, though we do use graphs to talk about any sort of pairwise connection between points, people, any sort of model that is represented in this way, where we call an edge, like that one down there in the bottom right corner, a loop, because it goes from a point to itself. It loops back around, as we can see there. And this is the notation that we need to know specifically for this class because we don't spend a lot of time with it, but we say a graph is simple if it doesn't have repeated edges, so we wouldn't have multiple going between 2 points, and we also don't have loops. Again, not too important for us, but I do want to point that out as well. There are a lot of details we can get into with graph theory, and we're going to be skipping over some of them to hit a few of the highlights. But again, the important thing to understand here is that with a graph, we're trying to model connections from one set of things to another set of things, or from one thing to a whole bunch of others at the same time, where we can talk about two graphs as being equivalent if they model the same connected set of relations, where in particular, because thinking abstractly like Euler did, how we arrange them, how we write them out, doesn't actually make that much of a difference in terms of what connections they show. So, if we have two graphs with the same number of points connected with the same edges, it doesn't matter how we draw them. Things like this up here will be equivalent because one is just the other pretzeled a little bit, and there's a little bit spun around like a twist tie in there. Or if we think a little bit more detailed, think with a little bit more points and lines, even two like this that look very different at first sight are still representing the same connections, so we call them equivalent graphs. Any pair of graphs that have the same vertices with the same edges are equivalent. No matter how you might want to rearrange them, you're still talking about the same things, so it's still the same picture, even though it isn't really the same picture. Anyway, that's just a bit of a introduction to our notation here. So the next thing we're going to get is a couple of quick modeling examples. Even though I said, this stuff isn't meant always for the real world, it's still good to see how it can be used in the real world to build up some of that grounding, to build up some of that motivation if all my talk about stuff that you enjoy doesn't make you want to enjoy this. Nothing can be done with that, so let's get some examples.